Cool. Hi, everybody. I'm happy to be here today, and I will talk about the state of Datahike, which has two meanings. It's first like the state of what Datahike is currently in, but I will also try to give you an overview of how the state management inside of Datahike is functioning. So the purpose of this talk is basically I will try to take different angles. On the one hand, it's like an historical account of why things are what they are at the moment and where they're going. And on the other hand, I also try to give like technical motivations and try to give a systematic overview. So if this is not fully working out, if you have any kind of questions, feel free to interrupt me also and ask me directly. I'm not sure how we do exactly the time management. I will try to stay in 40 minutes that were initially suggested, but yeah.
That sounds perfect.
Okay, cool. So first of all, I want to say a few things about me. I come from Mannheim, which is an industrial city in Germany where quite a few things have been invented. Mercedes-Benz, the car has been invented there. The bicycle has been invented. Of course, things have been invented in many places. I'm not claiming that this is the only place, but this is a very pragmatic city in which I grew up with a lot of heavy industry like coal power plants, chemical industry, pharmaceutical industry, and so on. So I definitely have an appreciation for engineering and solving large-scale problems and seeing the technical issues in them. But I've also studied in Heidelberg, which is arguably like the most beautiful city in Germany. It's just 25 kilometers away, so you could see the coal power plant if you squint carefully at the horizon. And I studied philosophy, I studied cultural anthropology, I studied mathematics, and then computer science and computational linguistics. So I've studied for a little bit of time, trying to figure out what I'm going to do with my life and also what I should work on. So I have a deeper motivation. I will try to keep things technical and focused here, but you might have a sense when I'm going through the stuff that I'm where I'm coming from. I'm also the author of the replicative libraries. This is a set of libraries that I will go a little bit into later that are basically focused around distributed systems programming. At the moment, I'm a PhD candidate in my third year at UBC here in Vancouver. We can talk about probabilistic programming also at the end. And and the co-founder of Lambda Forge, which is the company who is coordinating the work behind Datahike and is trying to, we are doing mostly contracting, but we managed to basically get contracts around Datahike that secure some of the development. Okay, so the outline of the talk more specifically is first I want to motivate why even care about Datahike, why even care about Datalog, why even care at all in some sense. I will also give a little bit of a background of what specifically we did in replicative and how this connects to the later work. I will talk about Datalog in this context, and I will talk about Datahike specifically. I will talk a little bit about Datopia, just basically to point to possibilities for the future and also work we have done in this direction, and then I will give an outlook. So first of all, I assume this is very similar for most of you. But I actually worked out of my motivations. I tried to build a democratic tooling around 2011-12. I was at Occupy meetings. I was on the election methods mailing list where people discussed these tools. I worked on a tool which is called Motorola, which was developed by a Canadian. And I joined him, but I was a junior developer and I just learned basically Java. I only knew C++ and Java. And it took me forever to basically build web tooling back then, like just simple web interfaces with GWT. So this was cross-compiled to JavaScript, a little bit crazy, but it kind of works. So yeah, this was interesting. I dived into programming, but I felt stuck. I thought like, okay, if I ever gonna achieve anything bigger in my life, this is not a good programming model to write, especially concurrent code for web crawlers and aggregating information from all kinds of discussion media. It took me way too long to figure out how to build this and be confident that I have written correct code that doesn't have race conditions and other annoying problems. So this was for me like I don't know, productivity increase. I felt like I suddenly became a magical programmer. I could pick up all kinds of abstractions. It was so much easier. I was so happy. And this happened, of course, by factoring state from logic. So I had like a lot of small functions that I could just plug together, and I could build apps and could build like logic on my machine. Everything was nice and fine. But as soon as you think about you want to connect a lot of distributed systems, basically all the niceness of Clojure quickly goes away again. So you all know settings like this. So this is a very, like, it's imagined for a moment, we are just in Clojure land here. We have 3 hosts, host 1, 2, and 3. And typically what we would see in a standard setup, we just basically do messaging between these different hosts through some remote procedure call component, be it REST interface or some WebSocket interface or whatever. And that's, again, is on this level, these hosts are basically stateful objects. So now suddenly, despite the fact that you're locally in your nice functional programming environment, you lack a programming model for distributed setting. And then you have to manually figure out how to do, let's say, if host 3 wants to do transactions over host 1 and 2, do something consistent, consistent state update, that's a big mess. Like, you need to basically implement your own transaction protocol over this. And of course, there are plenty of solutions, but I'm just saying Clojure itself as a programming model doesn't necessarily solve this issue. So there was early on, for very good reasons, of course, where Chicky said that he developed Clojure to develop Datahike. So Datahike was proposed as an answer, as a very powerful answer. So here in the same settings, sorry, the line got cut off here, but these are the same 3 hosts. And here you have a setting where you now talk to a centralized entity. I just call it a serializer because its main job is basically to serialize and store all the different changes. And then you can do consistent reads of the different hosts at any time point and reason about your system. So in terms of Datahike, you can basically access the database. You can, of course, do this also with any other serializable system, like strongly consistent system, could be a SQL database or whatever. We will later see that Datahike is a little bit nicer than that in the Clojure setting. So what are the properties of Datahike? Datahike is a functional distributed database. It's distributed because its indices are durable, persistent, and a distributed data structure. So I will later talk a little bit more how these indices look like, but for now you can think of, if you've read some introductory tutorials to Clojure's data structure implementations, these are basically the same form. These are trees, and these trees are mostly not changed. And then when you add something to the database index, you basically create copies of paths in the tree that you then persist again. And this is how you encode changes and mutate the tree. So it's largely unchanged. It provides Datalog as a query interface. It's read scalable, for example, on AWS. Now I think it's mostly focused on AWS. And the most important idea for me personally when I saw this, when I saw the diagrams from Hitchhiker, is that it's a very decomposable design. And I think this is different what people mean with unbundled. It's not just basically accessible and you can take it apart, but it's really that the abstractions in themselves also make sense and can stand on their own. Like the index makes sense on itself. The Datalog query engine also works without the indices. You can basically take the abstractions apart. And also you could compose them in new ways, and it would be super exciting. The only problem is Datahike is closed source. So no way basically to directly change the internals and adjust or fit the database to a specific app and problem. The other problem is what Datahike only solves this problem for you in the backend. Its reach is basically limited. But if we are serious about distributed programming and what we do nowadays, especially with all the web clients flying around, all the mobile clients, we mostly have most of the machines and the peers in our network are actually in this client ring outside here. So here I've drawn again our backend that now has a nice serializer, and let's say Datahike solves our problem. Then this is all nice and fine, but you still have to write all the glue code basically and all the coordination to make these different clients talk properly to the backend. And So there was an answer, I think it was around 2014, of how to address this, which is called The Web After Tomorrow. It's a blog post by Nikita Prokopov, the author of DataScript, also known as Tonsky. So if you want to look into this, I can also share the slides later. I can find the blog post here. It's super well written, and it should give you a sense of how you can use this central serializer to send kind of datums that are scoped to these different clients over the wire to synchronize these clients. And what DataScript in general provided is it open sourced the atomic programming model. It provides a very lean data log in the front end, and we have inherited this and tried to keep it this way in Datahike as well. So you can just pull it in as a library. You just have to do a few setup calls where you describe like basically just the configuration, set up the database connection, and you're good to go. So it's a very, in DataScript, it's even a little bit leaner because you don't have to provide a configuration for the durable backends, but it's kind of necessary as soon as we add durability to the mix. So it's a very lean data log environment that has found its way in many front-end apps, including like apps like Roam, for example, that are fairly popular right now. It also spawned several synchronization projects following the Web After Tomorrow settings. So this was Statsync, Posh. I'm sure there are other ones now, but these are like older ones that exist. And they try to solve this problem of having a full system programming model. We came at this from a slightly different angle by working on replicative. So I particularly started on this. So let me explain how we arrived there and at Datahike. We worked on it around 2013. So the consideration is at the point was, okay, Clojure was somewhat stable and established. Most of the libraries that you could use, like at least core libraries, were somewhat established and stable. But ClojureScript just came out, I think, a year or two before. It was still a little bit like a bumpy ride in terms of debugging and so on and implementing things. But I really wanted to have abstractions that work cross-platform, especially because of all the I/O handling and so on. You don't want to have slight inconsistencies between your different implementations. So we tried early on to have a uniform interfaces for all the different I/O. And the only way to do this, if you want to address JavaScript runtimes, or not the only way, but basically the way that I think is by far the best way to do this in Clojure is through core async. So we build on core async. This also has a few drawbacks, and I'm happy to talk about this as well. But this allowed us to write the cross-platform code base for distributed state management. So the different building blocks, just to quickly touch on them because they are also used by Datahike. So this is this is because their abstractions are fairly simple and stand on their own. So this is just a key value document store which has similar semantics like get in, update in, associate in Clojure. So the only requirement that we have for the underlying store is that it can provide us with ACID properties on a key value basis. So each of the key value pairs are stored in a separate blob in the underlying store. And this is then later used by the index for the index fragments of the indices of Datahike. We also recently added support for compression, and we adding support for encryption at the moment, which will also make this nicer if you start to distribute your index. Also, let's say, to clients. Yeah, we have flexible backends, as you would expect, just to mention it, memory file system. We have IndexDB, that's what we use now for the ClojureScript support. We have SQL support. We had CouchDB. I'm not sure whether it should work at the moment. I have not seen people use this a lot. We have Redis as well. So yeah, it's super easy to implement these interfaces. It got a little bit more tricky with the compression and encryption, but it should not be hard to adapt it. People also provided DynamoDB and S3. We still need to update this. I will also briefly mention this in the end. The next thing is network I/O. This is addressed through an abstraction that just named the name for cable in German, just to make it easier to Google. Basically, I picked like German names for this. And the idea is of the abstraction, it's a little bit different than what other people do typically with server frameworks and middlewares and so on. It's a symmetric abstraction. So there's no difference between each peer. So a client has the same interface than the server. And you don't introduce this arbitrary kind of, in my opinion at least, arbitrary mismatch between server and clients. And the way this works is there is a bidirectional wire on both ends, and you just implement middlewares against this wire abstraction. And then you can intercept and inject messages into these wires depending on what you do. And I have a picture for this that should make it a little bit more clear. So the cool thing about core async, what would work for us in Replicative, is that there is a publish and subscribe implementation in core async. So this allows you to decouple all kinds of, so for each data type that we implement, I haven't talked about this yet, and this is not a main focus of this talk, but CRDTs are data types that are implemented by Replicative to be synchronized between different peers. So here you can see that if you have a peer A and a peer B, they negotiate through this mechanism a bidirectional, for instance, WebSocket connection. And then these are just a pair of core async channels, input and output channel. And then you can plug in these different middlewares that, for instance, here do a consistency check that the values are properly hashed. They fetch all the values that, for instance, you depend upon. You can also do pull hooks or whatever. Like this is Replicative specific, but I just think that this is a very useful network abstraction that we will probably make reuse of soonish when we start to replicate Datahike. So Replicative itself is just a set of middlewares. It uses the conserver for persistence. And in case, I will not talk about them too much here, but these are conflict-free replicated data types. So our early work was focusing on the hardest setting, I would argue, of distributed systems. This is where you can have concurrent writers that change the state on all of your machines, and you still want the full system state to converge eventually. So these data types provide this as you can think of it as an object-oriented abstraction. So an OR map is an observed removed map. So you can add things and remove them. It's basically what you expect from a hash map. There's a last writer wins register, which is somewhat intuitive. And this is a data type that we developed on our own for the system. This was also with what it started, which is kind of Git, but with auto syncing. So it's a CRDT that internally tracks conflicts, which sounds a little bit contradictory, but it's resolving all the conflicts on a network level and then just exposes them locally to you, and you can basically resolve those. So this is the whole system picture that we had, and these parts we probably can make use of for Datahike. And for me personally, also the reason why I started to work on the hitchhiker-tree and what Datahike came out of, kind of accidentally in a sense, is I wanted to have better indices for the storage. So the hitchhiker-tree is just a sorted map that you can store that's durable. So it's usable for all kinds of, again, it's an abstraction that stands on its own. If you want to build a distributed database or any kind of state management system, it should be very useful to just use the hitchhiker-tree to store your stuff. But the limitations that I came to realize, at least for me personally, working in several client projects in parallel to my master's studies, also with my friend together with whom I started the company, is that actually strong consistency is a much nicer model if you can have it. So it's much easier to debug. It's because CRDTs basically can change their state in hindsight at any point. So you never know whether the system is actually in a state that you can really rely upon. So even if you do everything correctly in the CRDT part, if you then have normal functions that compute values dependent on the state of your system, they basically compute some arbitrary snapshot of your system or use this as a base to calculate what they are doing. So I think it's still tricky to use this as a default. It's definitely interesting though, and I don't think it's not useful, but I came to realize that it's much nicer to have something like Datahike to start with, which has a nice query language and a nicer higher level interface. and a better default programming model that fits in many situations. The underlying problem that's a little bit more, I think, that I learned through my academic exposure to the CRDT community is that if you actually plug these CRDTs into each other, it's also somewhat tricky to think about if they reason about the values of each other, because they can change independently. Let's say you have a nest, you have a list CRDT, and you have some to-do items in this list. They can change kind of independently. Also, semantically, they might be connected. And that's funnily a thing you can solve with Datalog. So you can implement CRDTs with Datalog. And Martin Kleppmann, who built Kafka and has written I forgot the title of the book, but yeah, the important the scalable distributed systems book. He has also a slide deck I can share with you where I implemented CRDTs in Datalog. So it seems to converge, and at that point it was clear that we actually rather have a Datalog database. So what is Datalog? I assume that most of you have heard of it and have seen it before. Let me just briefly touch on the basics to have that covered. It's a subset of Prolog. So if you have tried Clojure, basically it's a restricted form of Clojure. It's similar to SQL also. It's a relational calculus. It is guaranteed to terminate, which is very helpful. It is nicer though, and I will show this as an example in a second. It does implicit joining through logic variables, so you don't have all this boilerplate clutter of SQL. It's very elegant to express recursions. And because it's a programming language, it's also, I mean, SQL is technically also a programming language, but I would say it's much nicer to compose queries and build larger programs in Datalog than it is in SQL. And in the Clojure community, this has been popularized through Atomic and DataScript. I think in general, even that might be true. So a lot of the Datalog literature, which is super interesting, which we are currently trying to read through in our reading group, is fairly academic, and only lately I think it's starting to be picked up more by industry. But it has applications in many different areas, like program analysis, points to analysis. GitHub is integrating it, like SAML got bought by GitHub to integrate their Datalog style tooling. People use it for all kinds of distributed queries on their Spark clusters or whatever. Like Datalog is very flexible because it's so simple. If you can express your problems in it, it's probably helpful because you can then redefine how it's going to be interpreted later. So here's a very simple example in the Atomic flavor, just to briefly explain this if you haven't seen it. So this, if you've seen SQL, this would be like select. So these are the logic variables that we're actually interested in. They will be in the result set. And then we have different clauses that do the joins. And this is kind of the cool thing here, that this is a logic variable that is introduced. So E is automatically being joined with all the E's here. So this is the same thing. So I say I want to have an entity that is named Peter, and that has an experience level of A. So there's a fresh logic variable that is now bound to all the possible experience values that Peter can have, that any Peter in the system can have. I also can evaluate here a custom rule in the system. So they would have to be provided as a separate thing. So let's say I have a library where is programming is a Datalog rule that I can invoke. This is how I can invoke this rule. And then in the end, I want to maybe know whether this programmer is senior or not. It's just a somewhat contrived example. I just wanted to show you basically how it looks like and how you can write down the logical constraints in Datalog. Okay. Does that make sense so far? First, I should maybe briefly touch base before I just rush through. Anybody, any questions? Okay, cool. Perfect. Everything's super clear. Okay. So I want to talk about a few of Datomic's Datalog ideas because they are relevant also for Datahike deals with this. So how does the underlying system work? The cool idea is, and that's not new in Datomic, but it's just that Datomic put these ideas into this specific configuration that Datahike is also following. So you can use triple store that is also used in the RDF space, which contains, or which has triples like this. EAB triples here, and this is a timestamp for the transaction when this fact was added. So this is a fact that basically says that entity 41 has for the attributes release name the value Abbey wrote. And then here for entity 42, you have multiple attributes here, and these are the values for those. And here you see again which transaction added those. If you store your data in this format and not in tables, you automatically get kind of like the maximum form of normalization, because each fact will only be stored once in your triple store, which is very nice if you need to do schema changes. Like the schema of Datomic is easier to change, I would say, than most SQL schemas. It's kind of much more flat in a way if you don't introduce additional abstractions. Okay, and you can also, again, I kind of stole this and referenced it here from Nikita. He did a very good work early on to motivate why Datomic is a good idea, and also why you should use DataScript and what the ideas behind it are. So the second cool idea I would say is you run your query engine on a distributed snapshot of the indices in your process. So since I had this, I don't want to go back to a normal database because I think it's stupid on multiple levels. You should be able to run your query engine inside of your process if possible. It's a much more reasonable default, but that requires, of course, that you can get a hold on an immutable snapshot. That's intractable in most databases that exist that have mutable indices, because you cannot hold onto those. There would be a very complicated coordination mechanism to have this in a distributed system, basically replicating all of the other problems and just pushing them onto you as a user. But if you have an immutable snapshot, then everything is fine and you can just do this. You have this very simple schema only for each attribute here, so you don't need to define any kind of tables. The attributes in principle, like if you provide them for an entity or not, is always optional at write time. So every field is nullable by default. And then basically you will make sure in your queries that it's actually there. And if you want to have additional constraints, then you need to provide a schema in front of Datomic. But Datomic's information model is similar to Clojure. It's kind of like it's friendly with respect to nils, with the assumption that in reality, most things can be missing sometimes. Missing data is normal. Okay, and the other cool thing that is super nice in combination with the query engine on distributed snapshots is you can join over separate databases that can potentially be in different systems. I haven't never done this with Datomic, like doing it over different systems. I don't know how it actually performs. If you do this, let's say on AWS in your private Datomic instance somewhere else, but there's no reason why it should be any problem. Why there should be any problem. And this is also what we really want to do with Datahike. Then you have an history index that's nice for auditing the system, and you can also have direct access to the indices. The indices are in the format that I just described, so they are actually fairly accessible. If you want to sweep over the index and like do a map reduce job or whatever, that's not difficult to hook into. Okay, so what is Datahike then? I talked a little bit about DataScript. I gave the motivation of how Datomic is trying to make important design decisions. And you can think of, for the sake of this talk, that Datahike is roughly, at least initially, this was very true. It was just DataScript with the indices being swapped out for the hitchhiker-tree. So instead of having the in-memory data structures, the thing that I could figure out in a few hours by just hacking and making the tests pass is I can plug this in and it kind of works. So if you have your own index data structure and you want to have DataScripts support an API and so on, you could do the same thing. You can also, of course, like fork Datahike and add additional backends. We have like a separate backend API where you can do this. But just to say this was a nice experience with Clojure in general. Like DataScript was fairly well factored. The hitchhiker-tree solved a specific problem for an abstraction that fit the memory semantics of Clojure well. Exchange just the data structure that fits into the memory semantics. Boom, you have your basically Datomic replacement. There was a pretty cool Clojure moment for me. So obviously we are really happy about DataScript because it provided this in-memory Datalog implementation that made it possible to create the initial prototype. It's very mature. You're probably all aware of this, but it also supports a few nice things of Datahike, like pull expressions. It has transactor functions that you can call. It is a schema on read database, which means that you can provide a few constraints in your schema, but they will only be verified when you read from the database. So you can always add stuff to the database, and then at reading time, basically, it will be verified, which is less restrictive than you sometimes want to have if you actually start to write the data to your durable index. The limitation is it just runs in one process. So you can access it from multiple threads, but as soon as you want to do something else, it's kind of limited. And it's also not clear how to get the indices out of the runtime. You cannot share it with other processes that are in your environment. So what we provided so far, and what we've worked on the last 2.5 years, is we have schema on write support, which is optional. So you can have the same schema definition that for the Datahike. We have added history support in the same way that is basically the Datahike compatible. We added multiple backends that are usable and added a configuration middleware, or like a glue code basically that maps the different ways you can configure your backends to Datahike and to the different parts. So now you are even able to just have a separate project where you implement the backends and you don't need to fork Datahike or change anything. You can implement your own durable backend. There's a Java API, which is kind of nice if you don't have Clojure available in your environment. We have added recently like faster transactions. So in the beginning, this was fairly slow because it was just literally plugging it in. But the hitchhiker-tree is a very specialized data structure that you need to treat right. So we had to treat upserts in a specific way, and that made it like 20 times faster. So yeah, we also factored out the parser. That's not super important maybe, but it's kind of cool that it made it into CLJ Condor, and I have automatically tooling for calls to DataScript, calls to Datalog databases. At least I think for DataScript, Datahike, and Datahike. And what we recently did, like around Christmas, and now it's kind of almost complete. Almost all tests are passing, so it's definitely already in usable state. Is a Clojure script support, so you can directly store your stuff in. And let's see whether this works here. So here we have a branch just to show this on the website. If you're interested in this, we're also working on a blog post to present it. But for now, this is a CLJS support branch. And I would be super interested if you have any kind of feedback. So this is describing here, you can set up a schema. I decided against doing live coding or anything like this because we don't have that much time. But in principle, like I think this code here should be fairly straightforward. Here's the configuration. Okay, we want to have IndexDB. That's the name of the IndexDB database. And then you can just interact with the normal functions. The only difference is you need to use the core async primitives. So when you have a query here, you need to deal with this, which is normal. You have like I/O that is side effecting in JavaScript. It can be a little bit annoying sometimes if you are used to DataScript. So it's also something we can discuss. Yeah. Okay, let me give you some technical details. If this is like too much for you, no problem. You don't need to understand these details for the talk, but I think it's kind of cool. So the hitchhiker tree itself is a fractal tree. Fractal tree means in this setting, it's a combination of two data structures. It's both an append log and a B+ tree. And the append log has an optimal performance as a write data structure, and the B+ tree has a provably optimal performance under some conditions for reads. So what you would like to do is kind of blend these two, and this is what fractal data structures such as the hitchhiker tree do. So you still have amortized inserts that are logarithmic, and the reads as well. Like you cannot cheat basically your way around it, but you can get a better logarithmic factor there, that in the same way that for Clojure, it feels almost like a constant overhead to have immutable data structures, makes inserts very fast. It also supports batched inserts, which is very important if you want to do a bulk like transactions. And I have tried to give a very detailed account. There's a talk from David Greenberg, who initially invented and developed the code base for the hitchhiker-tree before we picked up and added ClojureScript support. And now I've also like done a few extensions. Here's a blog post where I try to lay out all the details of how the implementation works and try to explain it. I can just give you here a quick impression. So this is directly created from the plotting code in the hitchhiker-tree repository. This here is the first index that you have, the first tree on the left. So ignore for now everything here on the right. So let's say this is your tree. You have here an index node and here 2 data nodes that contain just integers. So these are your values here. And the 6 and the 9 are pointers to other nodes. So this is the 6 basically says like everything lower than 6, you have to go into this branch. Everything lower than 9, you have to go here. And this is how you navigate the B+ tree. And then what the hitchhiker-tree does, it has these append logs. So these are the things that are listed here vertically. So these are the values 1, 2, and 5. You see they are missing in the numbers here. So they are still waiting as operations that will be propagated through the tree. So now we added 10 more numbers to the same tree. And then you can see this is the new tree here on the right. It now has 2 levels of index nodes and only 1 element in its top append log. These ones here are empty and they are all basically written, but it does a structural sharing of this part of the tree. So while all the other nodes had to be rewritten in this example, it's in that sense a bad example because it does only very little structural sharing, but if your tree is a little bit bigger, that's much better, but it does the structural sharing here. One thing also, these numbers here, they correspond to hash values of the values here, so also of the index nodes. So you can use those to, we use this basically to make the hitchhiker-tree a Merkle data structure that you can verify outside of your system boundaries to contain the proper values. So if you would sign these hashes, you would basically have the distributed index that you can even verify and use outside of your backend, let's say, or system boundaries. Okay. So obviously this makes it easy to replicate this index in any kind of immutable, in any kind of content addressable memory. So distributed hash table, key value store, whatever you like, you can do it, of course, in Amazon DynamoDB and in S3 and read scalable stores like this. Basically, you only need to, in most cases, you only need to send around the root. You only need to update your peers and let them know when there's a new root if you transact new data. So only this is mutable in a sense. And then you can broadcast the changes of the root, for example, through Kafka, through the DAT project. We did this, we demonstrated in a blog post. It's kind of nice. It looks a little bit like a toy and ridiculous, but actually I think the idea is very powerful, that you can use this also with the file system and just replicate with all kinds, like the way that we store the index is very friendly to file system replication and distributed file systems, because we just change the file that corresponds to the root and everything is immutable files, which keeps the file system happy. But you can also do polling depending on for the root. Let's say you have a node that just once a day wants to read the database to do some, I don't know, sensor update or whatever, then polling might be more efficient. The point is you can have a massively read scalable content addressable memory. You can put the hitchhiker-tree as it is in there, and you can just propagate these changes through some publish and subscribe or to some broadcasting mechanism. And this will also make it super nice for scaling with the ClojureScript frontends, because they run the query engine locally. They can deref the indices from the backend, but they can do all the hard work in the front end. So the only thing you need to provide basically is a cheap key value store that is scalable. It can also be IPFS. I worked early on with BitTorrent. I think BitTorrent is cool. File sharing is cool. It's a little bit illegal, but these are very scalable systems. So I think this is a solved problem of how to do read scaling when you have a data structure like this. So this is how the system roughly looks like right now. We are at the moment working on making the distributed connection management work and actually hook this up so that we can have the backend Datahike nodes also automatically like sharing their indices between different client systems, can be JVM or Clojure script. And what we are missing here still from like kind of the original topics that we covered is we don't have any way to do multiple writers. And we don't have a way to do permissionless databases. So we cannot basically store some data independently. Like if you want to go fully distributed and use this as a distributed systems paradigm, then this is also kind of missing, that you cannot have a database that is managed by multiple parties. So you would have, first of all, you need to have access controls, but you also, there is a space that is opened by all the blockchain solutions, which is basically saying, okay, you want to have a system that is safe against counterparty risk. And I will briefly talk about this. I don't want to talk too much about it, but initially I was a little bit like, I heard about Bitcoin first, I think 2011 or so, or 12. And it sounded interesting and cool, but also a little bit out of what they try to do. And often, like a lot of the things in the blockchain space are reinventions of things that have been done before. Especially in the database space, they claim a lot of things that I think are super hard to do. But nonetheless, they put emphasis on a few aspects of problems that we have today. Basically, the massive data silos, figuring out economic systems that allow us to have shared data resources and address this. And I met a few guys 2 years ago. We started to work on Datahike. It's got a little bit like, it lost a little bit of its momentum, but I just want to talk briefly about the ideas, and maybe somebody of you is also interested in this. I would be super happy to talk about it. So what happens if you have, let's say in this distributed system, you have multiple parties that want to coordinate the access to a database, and then you can say, okay, we already have this immutable database. It's already auditable because I have added the Merkle hash, so the system is verifiable from the outside. And we kind of can deal with high volume data write operations. So at the moment we don't have any sharding, but we can at least like write 20. I can write 20,000 datums on my machine to Datahike at the moment, which is just this laptop here. So it's like compared to most blockchain systems and what they have in terms of throughput, this is starting with a database is much more reasonable than starting, let's say, with a JavaScript runtime like Ethereum did in a way. Like try to figure out a general purpose imperative programming language that you can run. So what we said is, okay, right now we cannot run Datahike in a permissionless setting, but it's just a transactor that needs to keep track of this publish and subscribe for the root nodes. So if we can establish a way to hook into one of these blockchain systems, then we would have Datahike as a blockchain automatically. And it's still, again, it's kind of very composable. And you can just plug in this transactor. So I've said already this is about data commons. I think this is something we are also interested in, basically how to build economies for apps or whole like social systems in the future. We talked about this a little bit here. That might be a little bit of too high level for you, but it depends. Like this is a motivation why to go in this direction. And so yeah, you can distribute a transactor with a blockchain. That's what a blockchain basically does. It allows you to decouple the physical machines from the logical notion of a transacting process by having this game of, let's say, the proof of work algorithm in Bitcoin. And what we then did in addition, what we have a library for that still needs to be released, is you need to have some logical rules that regulate how to write into the database. So I will not talk about this now because I'm short on time and it's also not super important, but this was the system that we prototyped where you could plug this into. And this should not be a capital D here. And this is kind of maybe more interesting. So our idea was, okay, why do all these languages have these funny transactor things to verify that inputs are valid? I think Datahike also came up with its own schema language. What we basically did is we have Datalog itself as a verification language for smart contracts. So you can imagine just writing the Datalog itself against the transaction data that's incoming, and if it unifies, it's acceptable. And then you can deploy contracts, and because it's terminating, it's a safe runtime, the query runtime is under control, you can lock it down. It's kind of a very nice system to play around with ideas like this. You still need to have the economic aspect of what the transaction costs, what is the incentives for the people in the blockchain system. This relates to how the transactor is working. But I think this is a very nice combination, and you automatically are composable with all other kinds of Datahike configurations. So in a situation like this, you would have these permissionless instances that are run, let's say, by some parties, maybe non-profits, that try to manage some data sources for you, or a combination of for-profits that basically establish shared rules of how they want to track and trace their data, let's say for the supply chain. And then you would have a system like this. This is basically where we want to get to in the longer run. Okay, so I'm mostly through, just like what with respect to the future in the near term, what you can expect is we are currently working on faster query performance. It's a little bit embarrassing that we are comparatively slow. So this is also partially inherited from DataScript. DataScript does not do a very sophisticated form of DataScript, the Datalog evaluation. So we are looking into this. We are looking into several papers also of what other projects do, like Souffle, for example, which is pretty cool. We work on attribute references, which is something that the Atomic has, the DataScript doesn't have. So Datahike is close to, this is like almost close to pull request or merged. We will have an extended migration tool that we are working on that will allow you to also import SQL databases, streaming migration. It currently can do Datomic to Datahike, but we also want to do this for Datahike to Datahike and other configurations. Obviously, we need more storage backends always. It's kind of a good thing to have. The garbage collector is almost ready. It depends on basically having these storage backends settled. And we are working on a browser-based dev tooling for Datalog, not just for Datahike, but also for DataScript, Datomic, potentially Data11, depending on the interfaces. And we do this together with our partner, who's also sponsoring our Clojure script work, which is Homebase. They try to provide kind of like a Firebase React front-end API with Datahike in the backend. So local first kind of approach to building apps, but for JavaScript developers with a very convenient API. Not a JavaScript developers Datalog is not intuitive for them. We figured out. So, okay, so the global address space, for me, this is a big thing. Like this is, I think, what also some of the RDF solutions want to go to. Although I'm not sure, I don't have experience in all the things that relate to what we do. There's a lot of stuff. So if you have also some experience or opinions, I'm very happy to hear what you think. I think they tried to do this for the semantic web, but they didn't have these nice databases, the Sparkle database and so on. I think at least up until now, were not the primary choice if you wanted to build a scalable app. I think Datomic has proven that it's very good to build just apps. So it's both a pragmatic and a principled combination if we can figure out how to create this global address space. What I mean here, this is not maybe super clear, but there are some papers from the Berkeley Distributed Systems Lab who did a lot of work with Datalog, including Bloom in Ruby. They have also some implementations where they do, for instance, pathfinding on a lot of systems. And the systems, the query engine basically looks up databases on the way while it's evaluating. So this is something that Atomic cannot do, but you can imagine you have all your databases in the global address space, or all the ones that you care about, stored as facts, the addresses of these databases themselves in Datahike. And then while you're running the query engine, it could basically look up these databases and do a recursive resolution of itself. And they could implement quite a few distributed systems algorithms that way. So I think it's a pretty cool direction to go into, especially from the Datalog angle. CRDTs, yeah, that's obviously necessary if you want to have clients that can write first locally, not just optimistically, but are guaranteed to succeed. We have some ideas about this. As I said, like Datalog itself is very useful to implement CRDTs. A lot of the internals of asynchronous Datalog engines look like they do some CRDT reasoning, at least one of the papers that we read. So we try at the moment to figure out how to make Datahike able to have a fully peer-to-peer setting as well, if your data schema allows this. So you will be able again to have eventual consistency and a kind of like centerless or decentralized setup. The other thing is we need to improve, as I already said, we improved the DataScript inherited query engine at the moment, but it is a fairly, like, it's nice for hash map replacement in JavaScript for a small library that does Datalog for you in the browser. It's not up to the task to be competitive with any state-of-the-art Datalog implementation. So we read a few papers. And what we want to do is we also want to go beyond Clojure. So we will try to standardize and type the interfaces to the index, the interfaces to the iterators, to some of the API calls, probably around Eden and JSON-LD, and then provide a way to implement the runtime itself in a portable, maybe in a portable Lisp, in a subset of Clojure that is compatible with Julia, Carp. Python has a Lisp dialect that I use, which is Highlang. Maybe we can figure out how to basically have something so you can keep your query engine even in other environments running in the process and get all the benefits of having access. There's also differential Datalog, super cool, incremental fluke maintenance that should be integrated. And yeah, these are some of the related like technologies. The FIQ thing is functional aggregate queries. I can also point you to the papers. This is very heavy in terms of math, but it's a state-of-the-art implementation from relational AI. These are the guys who bought like the differential Datalog people from Clojure for 3DF. And also, just to mention this, and also Chris Granger is now working with relational AI. So this is where a lot of the Datalog people went. But I still think there should be an open source solution that solves all these things. So let's see how far we can get. Yeah, you can also combine probabilistic programming. This FAQ framework also does this. And it does this in a very specific way, like it's not general purpose, but obviously there is an interesting intersection. You can also use Datalog inside of probabilistic programs. So yeah, but I don't want to talk about this today. I want to thank a few of the people that are involved. This is just a few of them, of course. In particular, David Greenberg, who did like the hitchhiker-tree, Nikita, who did the DataScript, my friend and colleague Konrad, who was working with me on Datahike and on the company. Wade, he recently did the ClojureScript stuff. This is the collaboration with Homebase that I mentioned. And these are like, obviously I need to thank Rich Hickey, no doubt about this. Would not be here without him. So yeah. And the way we get support at the moment, just to be a little bit, we try to be accountable as an open source project and be mostly funded. So we set up GitHub sponsors lately, Open Collective. We got funding through Clojurists together, which was super nice. That helped us to get the tuple support in and also improve our performance. This I already said. And the Swedish government, we have a long-term contract with the employment service because they're using Datahike in production as a replacement for the Atomic. And they fund a lot of the work as well. So feel free to join our Discord channel, and there we have a lot of like reading group discussions, and we are currently building up our shared like programming sessions. Yeah, so that's it.